Welcome to the video on how to write your lab report for Experiment 9, Introduction to Volumetric Techniques II. In Part A of the experiment, you will learn the proper techniques of using a burette. First, the burette is acclimatized using the solution that the burette is dispensing. Fill the burette close to the 0 milliliter mark with this solution. Check for air bubbles near the burette valve and tip and check for leaks. If there are no air bubbles or leaks and the bottom of the meniscus lines up with the burette scale, then read and record the initial burette reading. Review the video for Experiment 2 on how to read the burette. Place an Erlenmeyer flask under the burette. Open the stopcock to dispense some of the solution into the Erlenmeyer flask. Record the final burette reading. The volume of the solution delivered into the Erlenmeyer flask is equal to the final burette reading minus the initial burette reading. In Part B of the experiment, 10.00 milliliters of an HCl solution with known concentration will be pipetted into an Erlenmeyer flask. It is titrated by adding NaOH solution from a burette. This titration will be repeated until good results are obtained. It may be helpful to review the video on the use of a volumetric pipette and the video on titration. The aim is to achieve titration volumes to within 0.1 milliliters of each other, consistent light pink endpoints with each trial, and a titration volume that is within 1% of the true titration volume. This is an example of what the raw data may look like. The results of 4 titrations are shown. Note that all the volumes are read to 2 decimal places. The titration volumes used in this and the following examples are for illustration purposes only. Since the concentrations of the acid and base used in the lab will be different than in these examples, the actual volumes found in the lab may be significantly different than those shown in this video. First, calculate the volume of titrant, NaOH, used for each titration. The volume used is the final burette reading minus the initial burette reading. Only the good titrations should be used to determine the average titration volume. Consistent titrations should result in volumes that are within 0.10 milliliters, and pale pink titration endpoints are achieved. Trials 1 and 2 are within 0.10 milliliters of each other, but both of them are titrated to a darker red color than that which is desired. These are not ideal candidates to be included in the calculation of the average titration volume. Trials 3 and 4 are also within 0.10 milliliters of each other, and their endpoints are the desired pale pink color. In this example, trials 3 and 4 are used to calculate the average titration volume. The average of 10.03 and 9.99 is 10.01. When considering which trials to use, remember that errors introduced during pipetting will not show up as a poor color change observed at the titration endpoint. This is an example of what the raw data may look like. The results of the 4 titrations are 15.24 milliliters, 15.39 milliliters, 15.27 milliliters, and 15.21 milliliters of NaOH used, and all the titrations give a nice pale pink titration endpoint. Trials 1, 3, and 4 are all within 0.10 milliliters of each other, but trial 2 is outside this range. Perhaps slightly more than 10.00 milliliters of HCl was erroneously pipetted into the Erlenmeyer flask in this trial. In this case, trials 1, 3, and 4 are used to determine the average titration volume. The average of 15.24, 15.27, and 15.21 is 15.24. This is another example of what the raw data may look like. The results of the 4 titrations are 15.24 milliliters, 14.52 milliliters, 14.62 milliliters, and 14.42 milliliters of NaOH used. Trial 1 has a red endpoint and its volume is significantly more than the other 3 trials. As a result, Trial 1 can be discarded. Trials 3 and 4 differ by 0.20 milliliters, but both are within 0.10 milliliters of Trial 2. Since Trial 3 has a darker endpoint, it is also discarded. In this case, Trials 2 and 4 are used to determine the average titration volume. The average of 14.52 and 14.42 is 14.47. Using this average titration volume, the percent error of the titration volume can be calculated in the following slides. From slide 6, The concentration of HCl used in the titration is 0.1067 molar. From slide 3, the volume of the HCl solution used in the titration is 10.00 milliliters. The true concentration of NaOH provided by your instructor is 0.07423 molar. To calculate the true titration volume of NaOH, the balanced chemical reaction for the titration is needed. In this case, an aqueous solution of HCl and an aqueous solution of NaOH react to form an aqueous solution of NaCl and water. Since the balanced chemical reaction is 1 mole of HCl to 1 mole of NaOH, at the equivalence point, the moles of NaOH added from the burette must be equal to the moles of HCl initially present in the Erlenmeyer flask. Therefore, the true titration volume is given by the volume of HCl times the concentration of HCl divided by the concentration of NaOH. In this case, the true titration volume of NaOH is 14.37 milliliters. Review the Experiment 3 video on how to carry out a percent error calculation. From slide 7, the true titration volume is 14.37 milliliters. From slide 6, the average experimental titration volume is 14.47 milliliters. Therefore, the percent error is calculated to be 0.70%. In this example, the percent error is less than 1%. Therefore, the lab objective for titration accuracy is achieved. The first lab question has to do with calculating the concentration of a solution when a certain mass of a compound is dissolved in a given volume. The expanded roadmap for mole, mass, volume, particles calculations is a useful place to start. Molarity is the solution's concentration in units of moles per liter. The mass of the compound in grams needs to be converted into the moles of the compound. The molar mass of the compound is the conversion factor needed for this calculation. The volume of the solution must be expressed in liters. Then the molarity is the moles of the compound divided by the volume of the solution. Remember to keep track of the number of significant figures in the calculation. Consider this sample problem, which is very similar to the lab question. In this case, 50.1084 grams of potassium dichromate is dissolved in enough water to make 250.0 milliliters of solution. Since molarity is moles per liter, the approach is to convert the 50.1084 grams potassium dichromate into moles of potassium dichromate. The molar mass of potassium dichromate is needed to do this. Using a periodic table, the molar mass of potassium dichromate is found to be 294.185 grams per mole. Note that the molar mass should have at least the number of significant figures as the mass of the compound. Now the moles of potassium dichromate present can be calculated. It is found that 0.170330 moles of potassium dichromate were present. What is the volume of the solution? There are 1,000 milliliters in 1 liter, so 250.0 milliliters is equal to 0.2500 liters. The molarity of the solution is 0.170330 moles of potassium dichromate divided by 0.2500 liters, which gives 0.6813 molar potassium dichromate. Remember to watch your significant figures. It may be useful to review the videos on significant figures. The second lab question has to do with calculating the concentration of a solution from titration results. Breaking a problem like this down into a series of steps can be useful. The following steps can be used. The balanced chemical reaction for the titration must be considered. From this, the mole ratio between the reactants is obtained. How many moles of HCl was used? This can be calculated from the concentration of the hydrochloric acid solution and the volume of the hydrochloric acid solution used. By using the mole ratio of the balanced chemical reaction for the titration, the moles of the hydrochloric acid used can be converted into the moles of calcium hydroxide initially present. Convert the volume of the calcium hydroxide solution into liters. Dividing the moles of calcium hydroxide by the volume of the calcium hydroxide solution will give the concentration of the calcium hydroxide solution. Remember to watch your significant figures. Consider this sample problem, which is very similar to the lab question. In this case, 115.79 milliliters of a 0.08471 molar sulfuric acid solution is needed to titrate 27.58 milliliters of a potassium hydroxide solution. The balanced chemical reaction for the titration is 1 mole of sulfuric acid reacts with 2 moles of potassium hydroxide to give 1 mole of potassium sulfate and 2 moles of water. Note that each mole of sulfuric acid reacts with 2 moles of potassium hydroxide. The moles of sulfuric acid can be calculated from the sulfuric acid's concentration and the volume of sulfuric acid used. This gives 0.009886 moles of sulfuric acid. Using the mole ratio from the balanced titration reaction, the moles of potassium hydroxide initially present is found to be 0.019617 moles. Since there are 1,000 milliliters in 1 liter, 27.58 milliliters of potassium hydroxide solution is equal to 0.02758 liters of solution. The concentration of the potassium hydroxide solution is then obtained by dividing the moles of potassium hydroxide by the volume of the potassium hydroxide solution. The concentration of the potassium hydroxide solution is found to be 0.7113 molar. Remember to watch your significant figures. It may be helpful to review the significant figure videos. Consult the conclusion writing guide in the lab manual for what should be included in the conclusion. The conclusion should include a description of what these terms mean and how they are related to this lab. Write the balanced chemical reaction for the titration and include the physical states of the reactants and products. Summarize what has been determined in this experiment. Include the volumes and concentrations of the acid and the base. A table may be useful for this. Comment on the titration techniques. When reporting the results, make sure all the numbers are reported to the correct number of significant figures and units. This is the end of the video on how to write your lab report for Experiment 9, Introduction to Volumetric Techniques II.